Hi, welcome to the solution to problem 12 of the post-midterm 2 practice review. In this problem, we're given a symmetric matrix A, and we're told that A can be diagonalized into V lambda V inverse, where V is not an orthogonal matrix. So why is the above statement not a contradiction of the spectral theorem? Well, the spectral theorem tells us that any symmetric matrix A can be diagonalized into the form Q lambda Q transpose, where Q is an orthogonal matrix. However, it doesn't state that this is the only way to diagonalize A. Therefore, there being an additional way to diagonalize A as given in the problem premise doesn't contradict the spectral theorem at all. The next question asks, what's the name of the process that allows us to convert a collection of vectors into an orthonormal basis? The name of this process is the Gram-Schmidt process. And applying it to this problem would work as follows. Given some linearly independent set of vectors, v1, v2, and v3, we're using 3 vectors here because it's a 3x3 matrix. If we wanted to turn it into a set of 3 orthogonal vectors, u1, u2, and u3, we would take the following steps. First, the first vector, u1, would just be the original v1. This is the trivial step. The second vector, u2, would be the original second vector, v2, minus the projection from v2 onto u1. And then our last vector, u3, would be the original third vector, v3, minus the projection from v3 onto u1, minus the projection of v3 onto u2. So now our last step, find the matrices Q and lambda such that A equals Q lambda Q transpose. Well, lambda is just going to be the same lambda that's given to us in the problem premise because the eigenvalues are always going to stay the same. So we need to find the matrix Q. Now we want to use the Gram-Schmidt process here, and it looks like it's going to be a lot of work, but if we take a closer look at the matrix V, there's actually a lot here that reduces the amount of work that we need to do. Let's start with the quick recap of what the projection formula is. The projection of a vector v onto a vector u is defined as their dot products minus the length of u squared, and we scale u by that amount. So off rip, the first and second columns of V and the first and third columns of V are orthogonal to each other. We can verify this by taking their dot products. If we take the dot products of the first and the second column, we get 2 over root 18 minus 1 over root 18 minus 1 over root 18 equals 0. If we take the dot product of the first and the third columns, we get 1 over root 18 minus 2 over root 18 plus 1 over root 18 equals 0. And the second and the third columns are not orthogonal to each other. If we take their dot products, we get 2 over 6 plus 2 over 6 minus 1 over 6 equals 1/2. So what does this mean in terms of the Gram-Schmidt process? Well, this means that we can choose our u1 and u2 to be the first 2 columns of V because they're already orthogonal to each other. And that means that we only have to do the very last step of finding u3, where our v3, the original third vector, is going to be the third column of V. And since our u1 and v3 are already orthogonal to each other, we can disregard the second term, meaning that all we have to find is v3 minus the projection of v3 onto u2. So let's calculate that projection. Now, if we take a closer look again at the vectors of v, we'll notice that they're all actually also unit vectors. For example, if we take each of the components of the first column and square them, we would get 1 over 3, 1 over 3, 1 over 3. Add these together, and you get 1, and the square root of 1 is 1. If we do the same for the second column, we would get 4 over 6 plus 1 over 6 plus 1 over 6 equals 1 again, and the same would also hold for the last column. This means that we can, once again, basically disregard the denominator of the projection formula, giving us just the dot products of our two vectors, scaling u2. So we've now found that the u3 that we're looking for is equal to our third column minus our second column scaled by 1/2. Oops, these are supposed to be 2 root 6s. All right, now that we found our u3, there's still a little bit of work that's left to be done, because let's try to find the length of u3 and see if it's a unit vector. The length of u3 is not 1. In other words, we want to divide u3 by its length in order to get it down to be a unit vector, and we can finally complete our orthonormal set. And with that, we found our last vector, so let's put everything all together now. Our q is going to be the first column of v, 1 over root 3, 1 over root 3, 1 over root 3. The second column of v, 2 over root 6, negative 1 over root 6, negative 1 over root 6, and our u3 that we just found. So 0, negative 3 over root 18, and 3 over root 18. Our lambda is going to be the exact same lambda as it was before, 6, 3, 3 as the eigenvalues on the diagonal. And with that, problem 12 is done. Hope this helps.